start the.
Okay, great. Here, let me go ahead and share my screen. Can you see my screen?
Yes, I can.
Excellent. Hi, I'm Scott Callaghan. I'm a computer scientist at the Southern California Earthquake Center, which is based in Los Angeles, but I actually work remotely from Reno, Nevada. I'm going to be talking to you all today about CyberShake data access. So I appreciate you joining. I know it's getting kind of later into the afternoon, but I'm glad you're here with me today. I'm giving this presentation, but the CyberShake project has been around for about 15 years. And there are dozens of both computer scientists and seismologists who have worked and contributed to the project as a whole. And so I just want to acknowledge that this is kind of the work involved to produce the data that I'm talking about today is a massive group effort. So just to kind of give you a sense of what we're doing, I'm going to start with a brief overview of the CyberShake platform. I know some of you may be familiar with it, but some of you may not be. And so I just want to make sure that we're all on the same page. I'm going to talk about the available data products that have been produced by that platform and describe the data access tool, which is the focus of today's training, to allow you to access those data products if you're interested. We'll then transition from slides to doing some hands-on training. We're going to use Docker again. Those of you who were around this morning have probably got some experience with it. And I know Phil, before the session, kind of went over the instructions again. I've also provided a link here to the Docker setup if you haven't done it. If you need a copy of these slides, by the way, they're available through the HPS website. If you just go to today in the schedule and you find this talk, there is a link to these slides. I think there are a few other links in these slides as well. So if you have a local copy, you can then click on things. As we go through, please ask if we have questions. I mean, the point of this whole session, right, is to kind of hopefully be useful and help you see how you might be able to use this in your research. So, during the session, please feel free to ask questions on the Slack. I know some of my colleagues, Fabio and Phil, are monitoring the Slack and will let me know if there's anything for me. If you're viewing this after the session, then please feel free to drop me an email. I'd be happy to help. So I'll get started with a brief overview of CyberShake. So CyberShake is a software platform produced by the Southern California Earthquake Center. And so it performs 3D physics-based probabilistic seismic hazard analysis. So we're doing PSHA through simulation. And so this is an alternative to kind of the traditional approach, right? The traditional approach for PSHA is to use ground motion models, right? These are models that have been developed by taking empirical data and doing curve fitting essentially. And so these models, these traditional models, work by putting in the magnitude of the event, some distance metrics, some information about the velocity structure, so VS30, Z1.0, Z2.5, these kinds of things. And then you end up with an estimate of ground motion and some uncertainty. With CyberShake, we use an alternative approach to try to estimate ground motion, and that's to run wave propagation simulations for large suites of events. And so by doing this, we're able to capture phenomena that's difficult to capture with the GMM. So for example, we're kind of better able to capture basin effects because we have a representation of the whole structure rather than just a couple of metrics. Directivity effects from ruptures is something else that CyberShake is usually better able to capture because there's not a lot of parameterization of that in the GMMs. And so this is an alternative approach to doing PSHA. So the upside is we think we can capture some of these physical effects better. The downside is that in order to run CyberShake, you need access to high performance computing resources, and it takes a lot of time. A typical CyberShake set of simulations can take tens of millions of processor hours and like several months of actual wall clock time. So with CyberShake, what we do is we pick a location of interest, say downtown Los Angeles, and we then take an earthquake rupture forecast, which has a list of all the earthquakes that we're interested in considering. What we do usually is we go out 200 kilometers from our site of interest, and we select all the events where at least some part of the rupture surface is within 200 kilometers and are magnitude 6.5 or greater. Typically speaking, for a single location, we're looking at over 600,000 different events that we then simulate in CyberShake and obtain ground motions for. That's for a single location, for downtown Los Angeles, for instance. With CyberShake, what we do is we usually run then hundreds of different locations around a region, so we can end up with understanding kind of regional hazard as well, not just a single location. We've performed CyberShake calculations all up and down the California coast, as you can see from this hazard map over here on the right. But the results that we'll be talking about getting access to today are for Southern California, so kind of for this chunk down here. These results are kind of the latest and greatest. We finished the calculations that produced these results just in April. To get into a little more detail about like numerically what we're actually doing, we start with UCVM. So this is the tool that Phil and May talked about in the previous training that allows you to query the community velocity models. And so we use UCVM to create a velocity mesh for a region. We then use that as input to the AWP ODC wave propagation code, which calculates strain green tensors. And then from that, we produce low frequency seismograms from up to 1 hertz. One of the inputs to these seismograms, right, has to be the information about the event. And so we start with a earthquake rupture forecast for the results I'm talking about today. This is USURF2. But the earthquake rupture forecast only specifies a fault surface and a magnitude. So it doesn't, for instance, tell you where the hypocenter is or what the slip distribution looks like. But you need those things if you're going to actually simulate an earthquake, right? So we take this description from the earthquake rupture forecast, the fault surface, and the magnitude. We pass it through a kinematic rupture generator, and we end up with a bunch of different events, right? A bunch of fault surfaces that have a hypocenter somewhere and a specific slip distribution. And then we use these to generate our seismograms. From the seismograms, we then produce intensity measures, ROTI50, PGA, PGV. ROTI50, if you're not familiar, so it's a spectral acceleration measure. What you do is you take your 2 horizontal components and then you rotate in 1 degree increments and you calculate the spectral acceleration at a variety of periods. And so you end up with 360 values, 1 for each degree. You rank order them and then you pick the median. That's where the 50 comes from. It's a 50th percentile. So it's essentially an average measure of ground motion. It's kind of like geometric mean. From all these intensity measures, we can then combine them with the probabilities of each event happening, which comes from the earthquake rupture forecast, and produce aggregate data products. So for instance, for a single location like downtown LA, we can produce a hazard curve, which relates the amount of shaking to the likelihood of getting that much shaking. And then we can also produce regionally a hazard map. So for instance, each little white triangle here, I don't know how well you can see them on your screen, but each little white triangle here is a location for which we've performed the whole CyberShake processing scheme. We have then enough density that we can produce a regional hazard map for Southern California. Sometimes with CyberShake, we also are interested in synthesizing high frequency ground motions. As you notice here, we stopped at 1 hertz. And so what we do is we use some of the modules from the broadband platform. So Fabio talked a little bit about this earlier this morning to use a stochastic approach to simulate seismograms up to 50 hertz. And then we can combine those with the low frequency seismograms and produce broadband data products. So when we think about CyberShake, we really kind of have 2 different data sets that come out of this. One is the low frequency data set, and then the other is the broadband data set that includes both the low and the high frequency calculations. Before I go on, are there any questions? Okay.
I'm checking the Slack so far, and you're good, Scott.
Okay, cool. I just wanted to pause too because I know it's a lot of processing. The next thing I want to do is just define a couple of key terms so that as I go through this training and I'm talking about various concepts, I make sure that you understand what I mean. So when I'm talking about a model, I'm talking about a set of CyberShake data products usually for different sites that are all produced using the same set of input parameters. So they're all using the same velocity model, the same earthquake rupture forecast, the same rupture generator. They're essentially comparable, right? And so you can think of them as one giant data set. And so today we'll be talking about accessing data from the most recent CyberShake models, which were produced with what we call Study 2212, basically the CyberShake study that started in 2022 in December. And so we're going to be talking about both a low frequency model and a broadband model. For a site, I'm talking about a location for which the CyberShake results have been calculated. Like I mentioned, each one of these little white triangles on this hazard map represents a site where we perform CyberShake calculations. There are 335 of them in Southern California. CyberShake seismograms are all velocity seismograms, the units are centimeters per second, and they're all two-component. CyberShake produces a lot of seismograms. So for this most recent set of calculations, we produced about 420 million seismograms. CyberShake generates a lot of data. For an event, I'm talking about a single earthquake where we started with that USURF2 description of a fault surface and a magnitude. And then we have a unique hypocenter somewhere on it and a unique slip distribution. And so when we want to talk about an event, we can identify it through a combination of three numbers. The source ID, which corresponds to kind of what fault was it on, what's the fault section, what's its name. A rupture ID, which corresponds to what's the magnitude that goes with that particular fault section. And then a rupture variation ID, which uniquely identifies the hypocenter and slip. So with these three numbers, you can identify an event in the CyberShake catalog. There are about 720,000 total events in this study. As I mentioned earlier, for any particular site, we use a subset because we have that 200-kilometer cutoff, and so some events fall within that cutoff and some don't, depending on exactly where you are in the box. Also, each event has a source name that's assigned. So, the San Andreas or the Newport Inglewood, or kind of the traditional name you would think of that goes along with a fault. CyberShake produces a lot of different data products. And so that's what we're going to talk about today, right, is getting access to some of these different data products. Initially, right, we start with a hazard map. And then if you pick one of those dots on the hazard map, a single location, behind that is a hazard curve, right, which is site specific for a single site. You could then pick a location on the hazard curve and you could disaggregate it and say, okay, at this probability level, what events contribute most to the ground motion here? And then, you could look at the particular event. You could look at the seismogram that event generated at this site, or look at the intensity measures that come out of that. And so in today's training, we're going to talk about these three particular data products: the hazard map, the seismograms, and the intensity measures. To get the hazard map images is pretty straightforward. We calculate them in advance for you, and you can get them through the Wikipedia link for this study. We have a wiki page basically for the study that keeps track of a lot of the scientific and technical details that go into the study, as well as provides a link to the output data products. So if you're looking for hazard maps, or if you have some specific questions about, details about the inputs that we use for the study, these links are a good place to start. Seismograms, those are a data product that are available through the CyberShake Data Access tool. I'll be showing you how to get those in a couple of minutes. Intensity measures are also available through this tool. And obviously the seismograms and intensity measures are only useful if you know what you're looking at. So metadata is also an important component when it comes to retrieving this data. And so we have metadata such as, what site was this seismogram from? What are the coordinates of the site? The seismogram was produced from what events? What was the name of the fault surface? What are the extents of the fault surface? What was the magnitude of the event? And so all this is available as well through the data access tool. I should make it clear that because CyberShake is a kind of large-scale platform that requires sizable high-performance computing resources to run, what we're talking about today doesn't allow you to kind of perform additional simulations to get your own data. So in that way, it's separate from something like the SCEC broadband platform, where you can configure your own simulation and run something and 20 minutes later have some results. Because this is 3D simulation and it's large scale, we have essentially done these calculations already. And so what we're talking about today is ways that you can access this data which has already been simulated. So the data access tool, how does this work? So this is a pure Python interactive command line tool. This is why we will be using a command line interface through Docker container today instead of a notebook, is because notebooks are a little clunky when it comes to kind of direct interactive access with the process. And so the tool works by enabling the user to specify what kind of data you want. So you're expected to be able to answer a couple of questions about the kind of data you want. So the first is, what model, right? What CyberShake hazard model do you want data from? And so right now the tool supports two models. It supports the low frequency results and also the broadband results. The second question is, what data product are you interested in? And so the tool supports 4 different kinds of data. The first is site information. What is the name of the site? What are the coordinates of the sites? So you can kind of investigate which of these different locations are you interested in results for. Intensity measures, so ROTI 50 at different periods, PGA, PGV, seismograms, and then also event information. So, you know, a specific event, what fault did it occur on, what magnitude, what probability, things like that. The third thing you're expected to provide are filters. So the whole CyberShake data set is very large. And so you, typically speaking, you don't want to retrieve the whole thing. You're interested in a certain subset of it. And so the way that this tool works is you specify what filters you'd like to use to select just a subset of the data. So it could be something like, I only want the data for downtown Los Angeles. I only want the data for magnitude 7.5 and greater events, things like that. I should say these filters are inclusive. So the way that it works is essentially you say what data you do want with your filters, and then everything else is excluded. So the way the tool works then is it asks you these questions about the model, the data product, and the filters you want if you want your data sorted. And then once you've done that, behind the scenes, it goes and it queries a CyberShake database to retrieve the data and the metadata that you asked for. And then that information is then written to a file on your local storage. If you also want seismograms, then the tool will go off and download seismograms. They are stored in a Globus shared storage location at USC. And so those seismograms will then also be downloaded to your local system. Because the data set is pretty large, the tool will let you know how much data match your filters and you're about to download. So the entire study is about 70 terabytes of data, which is probably more than you might anticipate processing. And that's why then the tool will let you know how much it is, and there's a configurable parameter, and essentially if you are asking to retrieve more data than that, it will not let you. So you don't accidentally fill up your file system with more data than you were expecting. The data is stored in large bulk seismograms, so those bulk files are downloaded, and then the specific ones you want are extracted, and then the bulk ones are deleted. But it means that you might need kind of more temporary storage than you do to store the final data products. In addition to pulling down these data products, the tool also produces some files that describe your request. So that way, you make a request, you get the data, a couple of weeks go by, and now you've forgotten, wait, where did this come from? What site did I ask for? Did I put magnitude limits on it? I don't remember. So you have these additional files, which are essentially metadata about your request in the first place, to help you keep track of what you were looking for. I want to conclude with just a brief description of the formats that this outputs. You'll get to see this when we give it a whirl, but just as an overview, the metadata that the tool retrieves is coming from a relational database. And so as a result, that's kind of the format that it is output in. It's like a spreadsheet, right? You've got columns with different headers, and then each row is one entry with information. And so the metadata, therefore, is delivered in formats that are kind of like that. You can either pick to have it as a CSV, comma-separated file, and so that can be easily read through a spreadsheet, or you can write your own scripts to parse it and work on it. Alternatively, you can retrieve the metadata as a SQLite database. So if you're not familiar with SQLite, this is a database format that's entirely self-contained. So essentially your whole database is in one file. So you don't have to have like a database server or a special application or anything like that. It's just all in a single file, but then you can write database queries to pull data out of it. And depending on your application and what you're interested in doing, that could sometimes be easier. I should say that functionally, really, right, the point of this tool is to allow you to get access to this data so you can do clever and interesting things with it, right? It's essentially a massive data set of simulated events, some of which are quite large magnitude. I think our largest events are 8.45. And so over the years that we've done CyberShake, there have been a lot of really interesting and cool applications that have come out of it that we didn't originally intend. But when you have, a data set of 420 million simulated seismograms, there are a lot of, cool things that can be done. And so ultimately the point of this tool, right, is to enable you to pull out this data and then process it in whatever ways you see fit. Since the tool, some of what it's doing is querying a database, depending on exactly what it is asking for can affect how long that query will take. But if the tool has to go through a ton of different entries and figure out if it meets your criteria or not, that can take a long time, like 15 minutes or longer. And there isn't an easy way for it to predict how long your query is going to take. So if you're playing around with it and a query is taking a really long time, it does not mean that the tool is frozen. What it means is that the database is taking a long time to run your query. You can either wait, or if you're not feeling patient that day, you can kill it and submit a query that maybe will retrieve less data and will be faster. The ones that we're doing today for the training should only take a couple of seconds, so this shouldn't be a problem. Of course, now that I've said that, right, like I've just set myself up for failure, haven't I? It's the thing with the live demo. The last thing I want to talk about is the format of the seismograms that come out of it. So the seismograms are in a CyberShake native seismogram format. And so there's documentation on the CyberShake wiki. I'm not going to like go into a ton of detail, but basically they're binary files. They have a header followed by data. The header has information like what site the seismogram is for, the unique numbers that describe the event, the source ID, rupture ID, rupture variation ID. The DT, so what's the size of the time step in the seismogram, and the NT, how many time steps are there. So that way you can figure out how to read the rest of the file. And the data is just the X component followed by the Y component, because they're all 2-component. And it has NT 4-byte floats. I have links here to sample both C and Python code to read out the header and the data. So if that's something you need to do, that code may be a good starting point to see how things are formatted and how you can pull it out. So that's what I wanted to discuss kind of as overview slides. And so I'm just going to pause for a moment. Any questions before we transition to the hands-on part? All right.
I have a question, Scott.
Yes, Phil.
Will this tool be able to distribute results from other CyberShake studies?
Yeah, the intent is that this is a tool that we will continue to develop and maintain. And so certainly for CyberShake studies going forward, it will support access to those studies. In terms of other CyberShake studies that have been done in the past, if there's interest, then that's something that we can do. It's actually pretty easy to add support for new CyberShake studies.
Okay, good, thanks.
Should also say that this tool is just been developed. It hasn't been officially released yet. We're planning on an official release shortly, but kind of like Fabio's GMSV toolkit, we're getting everything set up so that we can do that release. But so you get a preview. So what I'm going to do, yeah.
I don't see any other. I don't see any other questions in the chat, Scott. So
okay,
okay to go ahead.
Great. So what I'm going to do now is I'm going to transition over to the tutorial. So I have a guide here. Let me paste links to it. So this is if you want to, I'm going to go through it myself, but if you want to follow along, let me put a link in the Slack channel. And I can put it in Zoom also. There you go. So I'm going to follow along with that. So you're welcome to follow along there too. But what I'm going to do is go ahead and run kind of the Docker commands that are there so that you can see what I'm doing. So obviously, if you get ahead or behind, totally fine. But please, if you run into issues, stop me, let me know what's going on, and we'll get things sorted. So I'm going to assume that you've got Docker installed. I'm going to start there. And ideally, you've already pulled down the container, so you don't have to do it now. If you do, it'll just take a couple of minutes. So I'm going to go ahead and fire up Docker here. Okay. And so the first thing I'm going to do is, if you do an ls, you'll see here that there are 2 directories. The CS Data Tools directory is the one that has the code that we're using. So I'm just going to run the tool with the help flag just to make sure that it's working. Excellent. So this is the help message. This is always useful, right? If you come back to this later or another time and you don't remember what's going on. But I was just doing that to make sure that everything is working successfully, and it looks like it is. So what we're going to do in this tutorial is we're going to run some common use cases, right? Go through some circumstances in which you might be interested in getting CyberShake data and explain how it works. So we talked about how CyberShake data is generated at a bunch of different individual sites, right? And I showed that map with all the little white triangles. But let's say, there's a certain location I'm interested in data for. I'm not sure where it is. I want to get more information about all of the sites that are available. So what I'm going to do then is retrieve a list of all of the sites that were part of the low frequency study. To help us keep track of our different data requests, because we're going to do 4 or 5 different data requests as part of this training, we're going to assign a label to each data request. So that's, if you see up here in the help screen, that's this option here where you can add a label. What that happens is that all the file names will be tagged with that. So then you can kind of just easily tell from looking at the file names which files go with which data request. So we'll use the label site info here. We'll go ahead and fire it up. So welcome to the data access tool. So it tells us we have these 2 available models. We have the low frequency one and we have the broadband one. And we're going to use the low frequency one for the training today. Then it gives us a list of the available data products. We said we're interested in site information. So we're going to do 1 here, site information. And then it asks us if we want to apply any filters. We don't, because we want the whole list of sites that are available. So we're going to say we're done adding filters. And then it's going to print out, this was our data product request. We asked for data from the low frequency model. The site info data product did no filters. And then it spits out here a couple of file names and tells us we're done. So let's take a look here at these files it tells us about. We see that it created 3 files. It created this one here that ends in a .json, this one here that's a .query, and this one here that's this .data.csv. So the first 2 aren't files that you need to interact with in order to get your data, but they can be useful if you forget exactly what it is that you were requesting. So if I take a look at the JSON file here with cat, you'll see here it has the model I requested, the products that I asked for, and the fact I had no filters. And so if I wanted to go back later and say, hey, wait a minute, I forget what the query was that I was using, I could pull up this file and I can see what it was. The query file contains the specific queries that are actually run on the database. So if you at some point run into a bug and you need to email us and ask us for help, please include the JSON and the query files as well as any error messages you get, because that makes it much easier for us to reproduce what you were doing when you ran into the problem. Now, let's take a look at the data, though, because that's really what we're interested in, right? So I'm going to use more here to take a look at this CSV file. And here we go. So I've got this header line. So this is the name of the site. We basically refer to all CyberShake sites using this 3 to 5 letter abbreviation, but they all have a long name too. And then we have the coordinates of the site as well. And so you can see, right, we've got lots of sites, which makes sense. Right? We know we have over 300. Okay, so we got this list of sites. Let's dive into one. Let's take the first one in the list. We'll take USC. Let's say that we're interested in learning more about particular events that affect USC. What we want to do then, and let's say we want to look at a subset of events that affect USC. So let's say we're going to take a look at events on the Elsinore fault that are between magnitude 7 and 8. So, okay, so we're interested in events. So we'll want to select the events data product. And we want to apply a couple of filters this time, right? We want to look at USC. We want to look at events between magnitudes 7 and 8. And we want to look at events that are on the Elsinore fault. So we'll go ahead and we'll fire up the tool again. Here we go. We should give it a new label, right, to help keep track of what we're doing. So let's call it USC Elsinore. Okay. So we're going to stick with the same model, the low frequency model, and then our data products. This time we said we want to get information about these events. So we're going to pick 4. We want event info. Okay. So now we see we have a different set of filters, right? We want to apply, let's see, magnitude. We said we wanted events between 7 and 8. So we'll add a magnitude filter. So that's 1. And then it asks, how do we want to specify values for the magnitude filter? We wanted to specify a range. So we'll do 3. And we want events between 7 and 8. Okay, great. We also only wanted events for USC. So let's add USC, site name, single value, USC. I think I did these two in the other order in the tutorial, but it doesn't matter what orders you apply the filter in. Okay, so and we also said that we want to only select events that are on the Elsinore. So that would be the source name filter, right? The name of our source. We're going to specify a single value, Elsinore. Okay. That's it. We're done adding filters. So I'll say we're done. And we're not going to worry about sorting our results this time. Okay. It's going to take slightly longer to query the database, but not too much longer. And now we're done. Just going to check. I see there's a thread on the Slack channel. Okay, good. It seems like we sorted it out. Excellent. Okay. So now let's take a look at the data we got here. We're going to use more again on the CSV file. So this time we've got it's different data, right? It's about the events, so it looks a little different. So the first 3 columns here, source ID, rupture variation ID. These are those 3 values that I mentioned in the slides we use to uniquely identify an event, right? So this points us to a single event in the whole kind of CyberShake catalog. It's on the Elsinore. This GI corresponds to a certain subsection of the Elsinore fault. I'd have to look it up. I don't remember like what the full name is, but this information comes from user. It's a magnitude 7.05, which is good. It falls between those 7 and 8 we asked for. This is the probability. Note that the probability is given at the rupture level. So in other words, the probability of all source 7, rupture 6 events is this. So if you wanted the probability of a particular rupture variation, you need to divide it by the number of rupture variations. And then these are the corners of the fault surface. You'll notice here that the magnitudes are the same for all of the events that have the same source ID and rupture ID. But if I go down here, you'll see that when we change from source 7, rupture 6 to source 7, rupture 7, we now have a different magnitude and a different probability. That's how the earthquake rupture forecast is set up. So we can see, right, if I go down a couple of times, I'm still at 0%. So clearly this is a large file. Let's see how many actual total events were retrieved. So if I more it and pipe it to WC, right, just short for word count, but it'll count lines as well with the -L option. We see I got 45,589 lines in my file. Since the first line is the header information, this tells me that there are 45,588 events on the Elsinore fault between magnitude 7 and 8 that were considered for site USC. All right, how we doing? Are we good? Any questions, confusions? Do you guys need a minute? I'll take a drink. You're good. I got a thumbs up. All right.
Looking good in the Slack. Yep.
We'll continue onward. Okay, so we got this list of events. Let's say I'm interested in learning something about ground motion for some of these events. Let's find out which of these produce particularly large ground motions. We'll say for the purposes of this training that large ground motions is 2 seconds spectral acceleration, 2 second ROT 50. That's more than half a G. So how do we do this with this tool? Well, we're going to want a different data product, right? We're interested in ground motions, so we're going to look at intensity measures. And we also need to apply a couple more filters, right? We said, in addition to USC, magnitude between 7 and 8, looking at the Elsinore, we want to look at 2 second ROT 50, and we want to look at values that are more than half a G. Okay, so let me let's fire up the tool again here. Well, this time we'll use a slightly different label. We'll do we'll add 0.5 G to it. Okay. Again, we're going to stick with the low frequency model. And this time we said we want intensity measures. So we're going to go with intensity measures. Okay. So we have site USC. So site name, single value, USC. Okay. We need magnitude between 7 and 8. So magnitude, we want a range 7 to 8. Okay. We need the Elsinore. So source name, single value, Elsinore. Okay. And now the new ones. We said we want 2-second period. So we'll specify the period, single value, 2 seconds. Okay. And then finally the intensity measure, right? So the amplitude, essentially the size of that intensity measure. We said we want it to be more than half a G. At this point, you can only specify a range. So essentially we want to do half in G and up to some large value that is unlikely to have actually happened, right, to capture all the data. So specify a range. The units are centimeters per second squared. So we'll do 490 up to, we'll say 10,000. There aren't any events that produce ground motions that large. We just want to make sure we include them all. Okay. We're basically out of filters. We don't care about site rupture distance, so we are done with filters. Do we want to sort our results? Sure. Let's sort them, and let's sort them in order of decreasing ground motion, so we can see the biggest events at the top. So that means we want to sort on intensity measure value, and we're going to sort in descending order. So now it's going to go off. It's going to query our data. It's going to take a little bit longer this time because the query is more complicated. And now we're done. Okay. So let's take a look at what we get this time. So if I look at the data file here, okay, so we've got a couple additional columns this time. We see that we start with something called the run ID. Every time we do a set of CyberShake simulations for a site, we assign it a run ID. So this is a unique identifier. This is useful if you are either trying to keep track of exactly which run this was pulled for. If you're trying to interact with somebody else about this, if you're like, hey, I was looking at the CyberShake results from run 9306, and if there was a problem and you wanted to email me, it's a way for us to make sure that we're all talking about the same set of CyberShake data that was done for this particular site. That's the site name, right, USC. Here are the, again, the source ID, rupture variation ID, the 3 values that uniquely identify the event. We see it's an Elsinore event. That's good. That's what we asked for. On these particular 3 subsections, it's magnitude 7.75. This is the probability. You can see this probability is a lot lower than the ones we looked at before. Right? It's pretty low. We're looking at 2-second ROTI 50. Here's the actual ground motion. So this is like 0.7 Gs, and then the units. One thing that's just the way the CyberShake models are set up, you'll notice that all of the magnitudes are something 5. That's just kind of the way it's set up. So for example, if for some reason you were interested in magnitude 6 events, we don't actually have any. We have some 5.95s and some 6.05s though. So that's just kind of a weird quirk. So here we don't have that many, right? If I more down, we see I only have a couple of pages worth of events. So let's say that, maybe I'm interested in actually looking at the seismograms for these events. So we can do that next. We can go in and we can pull out the actual time series that go with each of these events. I'll just pause for a minute and make sure you're all good. All right. So the last thing we're going to do then is actually go off and get these seismograms. So what changes? We're basically going to use the same filters because we want the same data. The difference is the data product, right? Instead of returning intensity measures, we want to return seismograms.
So Scott, can I ask a question? Just calibrate the group. How big is this seismogram, the collection of data of all the seismograms for one of these studies?
Yeah, the collection of all the seismograms for the low frequency is about 15 terabytes, and for the high frequency I mean, for the broadband, it's like 55 terabytes, I think. So
Okay.
yeah.
That's why people probably would come to you and say, can I get the seismograms for CyberShake? And say, sure, do you have 15 terabytes of storage? Okay, thanks, Scott. Just wanted to mention that.
Oh, sorry, Bella. Yeah, you can hit Q and that will get you out of more. Yeah, so usually if you're interested in working with like a large set of CyberShake data, what I usually recommend is that you retrieve a small sample first, maybe, more than a few gigabytes, and then get your whole kind of processing stream set up, analyze that data in the way you want to analyze it, make sure you're getting the results at a small scale that you expect. And then once you've got all that set up, then you can go retrieve larger quantities of data because now you've kind of got all your analysis sorted and you have the bugs worked out of it. So it's usually what we recommend for people that want a lot of data. All right, so we're going to retrieve seismograms. We're also, if I do an ls and take a look at the current directory, my files are starting to accumulate. So let's say I want to put my seismograms somewhere else. So I'm going to create a new directory. I'll just call it cleverly seismograms. And then what I can do is I can tell the tool to please put all the output files in this particular directory. So we're going to do that this time that we run it using the -o option, which is short for output directory. We're also going to give it a new tag. We'll call it a new label. We'll call it seismograms. And we'll do -o and then this output directory. Okay, good. All right, one more time. So we want the low frequency model. This time we want to retrieve seismograms. So data product 2. Okay. And now we're going to go through the filters again, right? Site, I'll do it a little faster this time. Site USC, magnitude between 7 and 8, the Elsinore source, 2 seconds period, ground motions larger than half a G, and I'm done adding filters. Sure, either way, it doesn't matter if you sort it or not. We can sort it again. We'll sort it on decreasing. We'll sort it on decreasing value again. All right, this time it'll take slightly longer because it's going to download the data as well. So you can see here, it tells you, right? It tells you the temporary disk space required to download seismograms is 86 megabytes. The actual size of the seismograms we're downloading are just 2 megabytes. This is because, as I mentioned before, the seismograms are downloaded in bulk. And so it's downloading kind of 86 megabytes of these bulk seismogram files, and then it's extracting out just the 6, it's downloading 6 bulk files, and then it's extracting out the specific ones that you need. And then once it's done with that, it will clean up that temporary space for you. So the kind of total final space that you're using is just this 2 megabytes. But you can see how that wasn't that many files, and we're already up to 86 megabytes of temporary space. And so you can see how it does grow quickly. All right, so I've got my data. Let's take a look at it. So if I do an ls on that seismograms directory, then I can see my files. So I've got all these individual seismograms, and then I also have these output files that we saw before. We see I have the JSON file that we talked about, the query file, a data.csv file, and we have one other file. This URL files. It's just a list of the OS. It's just a list of it's in the seismograms directory. There we go. It has a list of all of the URLs that were actually downloaded. So these are the URLs where the data was retrieved from, along with the specific rupture variations that were extracted out of each of these files. That's all that is. Okay, so I have these files here, and they say seismograms, but maybe you don't believe me. And you're like, are those actually seismogram files? So we're not going to, as part of this tutorial, we're not going to write code to specifically like extract or analyze the seismograms within, but I can briefly show you to prove to you that yes, there's something in it that looks vaguely seismic. We're going to use kind of a weird command. It's OD, which stands for octal dump. But basically it's a way to look at binary files from the command line. And so we'll just look at this first file here. And we're going to pipe it to more. And so what this is going to do is it's going to show us the contents of the file. Over here on the left is essentially, it's like a line count, but instead of being a line count, it's a byte count. It's how the offset, how far you are in the file. This is the header, which don't worry about it. What I want to show you here is this part, which is the actual seismogram data. So you can see it starts, basically 0, really, really small values, and then starts to grow. And as you continue to more down, you see it kind of gets bigger and then smaller and then bigger again. And then it starts to get quite large absolute values, right? Down here, you're looking at absolute values. Remember, the units here are centimeters per second is a velocity seismogram. So you see you're getting here in the, between the 100 and 200 range. And so then it continues to kind of oscillate as you keep going between negative and positive values. The magnitude becomes smaller. And then eventually, if you're patient enough to keep going, you'll hit the end of the seismogram for the first component, the X component, and you'll end up starting the seismogram for the Y component. And here it is. So the first component ends with a bunch of zeros, and then you transition to the Y component, which is the same thing. When you're done, you can hit Q to get out of it. So that's not how you would probably analyze the data, but I just wanted to show you that like what's in there is really a seismogram. So we see this seismogram, but maybe we want to go back and learn a little more about the event that created this seismogram. So we want to know, okay, what was the magnitude of this particular event? So what we can do then is we can look at the data file that was generated as part of this request. And so, hang on, actually, I'm sorry. Before I do that, which we have to figure out which event in the data file we're looking for. The seismogram name tells us what event it is. It tells us it's USC, it's a run ID 9306, it's source 17, rupture 6, rupture variation 40. So that's what we want to look for in this file, source 17, rupture 6, rupture variation 40. So let's see, and here we go. Source 17, rupture 6, rupture variation 40. And so we can see that this was a magnitude 7.55 event. What if I wanted to know how much ground motion it produced, right? I saw the seismogram, but what if I want to know what the 2-second ROT50 was for this value? Well, what I could do then is I could go back and I could look at the results from the previous step, right? The one where we retrieved the intensity measures. I still have those files. So I can take a look at the one where we retrieve the intensity measures. And I can look for that same event, source 17, rupture 6, rupture variation 40. And here it is, right? I can see here that it produced, a little over 0.6 Gs of acceleration. So those are the things that I wanted to demonstrate for you today. And I hope you're getting a chance to kind of try it through yourself. I know for me, at least, it helps me learn and understand better what I'm doing when I'm actually typing things on my own and like examining the files and such, rather than just, watching somebody else do it. You should also feel free to, run queries that aren't necessarily part of this tutorial. As I said, the amount of data we'll let you download is capped at 1 GB, so you can't go too crazy. And, feel free to, try different things if they're of interest. There's also a number of additional features. You may have noticed, for example, that there are flags and command line arguments and such when you ran the help that we didn't talk about here, and that was intentional. I just wanted to give you kind of a basic overview of how you can use it. But there are other things there as well. There is a link at the end of the tutorial to the GitHub repo for this tool, and the documentation there goes into some more detail on some of these other features if you're interested. You are also welcome, if you want to install it, locally on your own system if you think this is something that will be useful. And so there is additional information about that there as well. I appreciate you joining today and being guinea pigs for this. I hope this is useful, and I hope, ultimately that maybe there's some elements of the CyberShake data set that you're keen on investigating, and maybe you'll find something that nobody else has looked at before. That's kind of the exciting thing about having this large collection of simulated events. If you run into bugs or you have feature requests or questions, you can email us at software@scec.org. I'll hang on for the next couple of minutes just in case some of you are still working through it and you have questions either about the tool or about the CyberShake project in general or some of the science that underlies it. But thank you very much for coming.
Thank you, Scott. Very nice. So I'm going to grab the screen. We're approaching the end of our day today of our tutorial sessions. We very much appreciate all of you joining. Give a moment to see if there's any questions in the chat. We will include all the presenters will include their contact information in the workshop materials, and please feel free to we can reach our group, our SCEC software group, through software@scec.org if you have questions or interest in using these tools.
I think this was great. Thank you. Thank you, all of you, for this day. I was not there the whole day, but I caught really a lot of interesting things, and the tutorials were great. Thank you. It was really, really fantastic.
Very good. Thank you. So, Scott, you see there's a question in the chat?
Oh yeah, about copying seismograms from the container to the local computer. I know we had, I think, someone asked a similar question when it came to the PNG files that were produced with the GMS toolkit, I think. And so we came up with a couple of solutions. One is, I think, Docker. I'll have to take a look back in the chat, in the Slack. Let me see if I can find it. There's a Docker command, I think, that allows you to copy files from a container image out to the file system. So you can do that. I'll look back through and find it and then paste it over. And then, but like long term, right? If you were planning to do kind of large projects and you wanted to do this, the best solution is probably to mount a directory. And so what that allows you to do is it allows you to take a directory that's on, your normal system and mount it so that you can also see it in the Docker container. And then anything you put in that directory in the Docker container, even when you exit the container, you'll still be able to see on your normal file system. So that's the best solution if like you're thinking about, okay, I want to use this on a regular basis. How do I get things out of my container? But for the purposes of today, let me find that thread from earlier and see if I can find it. Yeah, it looks like there's a Docker CP command.
Yes, well, Scott's finding that. I just want to follow up that we originally set up the containers in the way Scott's describing, by mounting a directory that was shared between your laptop and the container. It's just slightly elaborates the command you use to start up the Docker image for simplicity and to make it easier for a group to do the tutorials. We left that out, but if you're interested, please email us. We'd be happy to provide. It's an easy update to provide to show you how to mount that container or the file, the directory in the container and on your local computer.
Okay, yeah, I think I put some things in the Slack channel for it. I replied to your thread. So you run Docker CP. You just need the container ID, which you can get from running Docker container ls, and then you need the path, the file system path in the Docker container, and then the file system path on your drive. And then what Docker will do is then copy the things from the container out. So that's a way that you can get things out from this tutorial. Here also, as I mentioned, we set it up as a Docker container because we wanted to make this really easy for everyone to use. And we knew that since we're already doing Docker for this kind of overarching training, you know, you're all going to be experts for the end of Friday, right? But there's also the option, as I said, if you're thinking about, okay, moving forward, I want to use this on a regular basis. There's also the option to install it locally if that's more convenient for you.
Right, and that would just require having a Python environment on where you install it, right?
Yeah, it requires Python 3.8 or newer. It requires one Python library, which is installable using pip, which is a kind of a pretty common and easy way to install Python packages. So the installation is really pretty straightforward. Since it's pure Python, there's nothing to compile or anything.
Okay, well, thank you again to all of our presenters. Thank you for all those that attended. We appreciate the interactions, the feedback and questions, and we very much like a community using the tools that we work on and develop. So we'd be happy to work with you if you think the tools would be useful for your research. So we really appreciate you attending and interacting with us on these tutorials today. So with that, we'll close, but I look forward to working with many of you in the future. So, thank you.
Thank you again.